I'm gonna, let's see, what's a good way to do this?
Any second now. Okay, there we are.
Looks
There
good.
we are. Hello, everybody. My name's Ronnie Heron. I'm your host, and I will introduce you to my fellow astronomy freaks here in a minute. It's the SBAU Astro Hour. SBAU is the acronym for Santa Barbara Astronomical Unit right here in Mudslide Paradise. Astro, of course, short for our real interest, both in our club on this weekly vlog as well, astronomy or astrophysics. Different members, some on the board, get together and kick this cosmic stuff around every week for a whole hour. First meeting of the month will be this Friday night, featuring at Farrand Hall, our old friend from Las Cumbres Observatories, Joseph Farah. He's a grad student on his way to a doctorate, and his talk will be Black Hole Explorer and the Edge of the Universe. And you better get there early. Last time he overflowed the place. This is program number 213, everybody, for March 31st, last day of the month, through April 6th. And let me tell you what we're going to talk about. We're going to find Ptolemy's star cluster inside Scorpio's Stinger. We'll have some elliptical galaxies in our eyepiece lenses. Our moon is in Gemini, catching up with Mars. It's going to hit its first quarter right before our general meeting inside Farrand Hall Friday. Boeing aircraft is getting a second chance with NASA for their Starliner capsule that you might remember stranded those two astronauts in space. European Space Agency probe called Hera has been launched back in October, taking pictures of Mars' two little moons, or at least one of them, on its way out to the asteroid belt. Will Sirius B explode as a number 1A supernova? And how prevalent, how safe will nuclear power be in space? Also, a summary of exoplanets and other discoveries. Let me introduce everybody. Now, my name's Ron, and here's Jerry. He's back, Jerry Wilson, our beloved president, in office, what, a year longer than me. I guess we've both been in there about 7 or 8 years through the pandemic. And he just got back from Eugene, where he fulfilled his duties up in Oregon as a grandparent by spoiling rotten his grandkids. Chuck McPartland is with us, Santa Barbara Outreach Coordinator, with his black cat, who will show up every so often. Both Chuck and Jerry are married to Pats. Pat Forgy is Mrs. Wilson, and Pat McPartland, who is married to the Outreach Coordinator, also runs our merchandise department and our treasury.
We're each married to a Pat.
Yeah.
What, say that again?
We're each married to a Pat.
I know that, and we're going to have to designate them 1 and 2 or whatever. Actually, Pat McPartland has something to do with parsnips, at least on her email. I'm not sure what that's all about.
My family, my sister's name is Bonnie, and my wife's name is Bonnie. So
okay, well, that's Bruce Murdoch. To my left, or no, to my right on the screen, his wife is Bonnie. He's president of the Santa Barbara Theater Organ Society, and he knows his stuff. Tom Whittemore joined us. He's the editor. There he is. Former Westmont College science instructor. His wife is Maureen. And Tim Crawford with his new computer.
Yeah.
Yeah, there he is. Telescope expert and longtime member. And my damn voice is in the shop again, and I got to use this loaner they gave me. We start the show every week. What?
A loner voice.
Yeah, these damn loaners are never worth anything. I'm just as well I retired from radio, but forgive me for, the croaky sounds on the tube here. We got a few sillies this week that we can start the show with, stuff that I used to call silly science cartoons. Jerry has sent to us, and we've got some thought provokers. This one, I'm not sure what comes.
The density of funny ones has gone down lately. So I did put in a few thought provokers here. So we have 2 of each.
Okay, well, we just started our 5th year, so the last 4 years of these programs is a great compendium. Yeah, this could be what, ancient Greek, or is this Carl Sagan talking, or are these the definitions in Oxford?
No, I don't think this is from anyone famous. It's just a good.
Well, it's right on target. Top one says religion based on faith, beliefs, and scriptures. The middle one, philosophy, is based on logic, critical thinking, and argumentation. And
Yep.
finally, there's Einstein's picture. Science is based on evidence, observation, and experimentation. You
Now,
know the only one missing?
when I was
What?
in the ninth grade, taking my first science class, we discussed philosophy and science and their relation. And the teacher said that philosophers in ancient Greek would spend a lot of time arguing about how many teeth were in a horse's mouth. And then
Really?
one day someone just decided, well, let's go over and look and count them. And that was the first scientist.
Oh, is that right? Well, you could put a fourth category on the screen. It'd be interesting to see what you'd write beside it, and that would be astrology.
That's under
based on-
religion and myth.
That's
Right.
under religion, yeah.
Right. Okay, this is good. All right, blow that sucker up. Was that the astronaut on the moon or?
Somewhere where there was a rover.
Yeah, he's talking to his robot rover either on the moon or Mars. Mission report. Rolling machine. Let's see. He says, mission report, he asked. And the machine responds, there's nothing out there, just rocks. And the human says, yeah, we're here to analyze rocks. Rover goes, oh. And the human says, you're called a rock analysis robot. To which the rover responds, well, doggone it, this changes everything. Can you guys see that? Yeah.
Yeah.
This one has an interesting comparison chart about meetings and the length versus your boredom. It does tend to rise. Attention span goes down, and then somehow, it's washed out. We don't get the snake on this one.
Oh, really? Okay, wait,
We
okay.
don't get the bottom. We don't get the bottom line, which is
It's
yellowish.
very faint, yeah.
To get the idea, I guess what's the word for it? The proclivity of him drawing a snake rises as it gets boring, and that's
There
why
we are.
Yeah, that never came out.
there it
This
is.
reminds me so much of how I feel during some meetings. My attention span goes down, my boredom rate goes up, and then I'm looking for things to do. So the probability of me doodling a snake starts going up.
Hopefully
Well,
that
was it-
hasn't happened here yet.
No, it wouldn't
Hasn't
happen
happened.
here.
Did in the old homeowners association, though, didn't it, when you were president?
Well, no, yeah, I was president. Those things were pretty raucous. I wouldn't say there was any boredom involved.
A lot of times there's a drama queen on every board, and I don't think we have one with
We
us.
have a couple, yes.
In quantum mechanics, this is Dr. Brian Greene. Quantum mechanics, we often say that a particle can be two places at once. It's more precise to say there are situations when a particle may not have a location at all, which is deeply weird and disturbing. That entangles me, I'll tell you right now, gentlemen.
Uh-huh.
Wow. We deal with the macro and the micro in this discipline, don't we?
Okay, let me get back oriented here.
All right, we're going to start our night sky view. Here we go, folks. Number 213 into our fifth year.
Now, this is a finder chart for an elliptical galaxy.
Jerry, may I mention something before you
Please.
get to this deep stuff?
What deep stuff? We never talk anything deep
Deep
here.
sky stuff, deep sky.
Oh,
So, got a couple of chances last week to see Venus, very easy to view in the morning sky.
okay.
In binoculars, it looks like a crescent, like a little smile
Yeah.
in the east. Still looking for Mercury, but then we got blasted by these, clouds and rain,
Mhm.
which is good.
Maybe it got swallowed up by the sun. Who knows?
No
The
chance.
Venus is easy now. It's very easy to see.
Okay. Well, now back to the deep space. Deep
Elliptical.
space.
What does that mean? They're fuzz balls, right?
Yeah, basically it's a fuzzball. Galaxies come in three kinds. There's a spiral, there's a barred spiral, and then there's an elliptical. And astronomy's been going back and forth to the point where I'm confused, but they make a tuning fork diagram of the evolution of galaxies. First, they just guessed at it, and they said that on one tuning fork you have the elliptical galaxy, or you have the barred spiral. On the other, you have the spiral, and they collide and produce these fuzzball things that have no obvious structure. And then I've seen articles where the evolution goes the other way. A spiral or an elliptical galaxy then collapses into a rotating disk of one type or another.
Yeah, but since ellipticals are mainly old stars and metal poor, that doesn't.
Yeah.
Do they evolve into rotating spirals?
Do they say that again?
Do the ellipticals evolve into rotating? Aren't
The
they?
problem,
Oh,
the
no.
problem with astronomy is that we can't look at some of these things and see what they do in their lifetime. So we have to look at other ones and say, is this later or is this earlier? And as Chuck just pointed out, the stars in the ellipticals are very old stars. So it's likely they are the end product.
Right, from mergers.
Yeah,
Likely.
from mergers. So here we are in the night sky. This is about 1 a.m. Actually, it's tonight, but that won't matter. This is the constellation of Virgo, and there's a lot of galaxies up here in Virgo, namely the Virgo cluster. My two favorite stars down here, Zubin el-Shamali and Zubin el-Ganubi in Libra. I'm tongue-tied here. Libra. More coffee. Serpens Caput.
Yeah.
And right in here is a Messier 5, a globular cluster. And right there is the elliptical galaxy, NGC 5846. Magnitude 11, you won't see it by looking up at the sky. You need a big scope to see it. A 6-inch will technically show you the 13th magnitude, but that's in a point. And this light is spread out over a thing, so you have no hope of seeing it at a 6-inch visually. This is a close-up of NGC, the elliptical galaxy, NGC 5846. And right next to it is a very interesting barred spiral galaxy, NGC 5850. And you can see the core and you can see the bars. And there are faint forget that. There's faint arms out here. So it's a spiral galaxy. They just don't show in this picture. Have any of you guys ever seen this visually?
No, I've never seen that. How far away?
Yeah, it's quite a ways.
It's going to be 30 to 50 million since it's in that neighborhood.
Yep.
Well, we can tell that spirals are turning. Are the ellipticals? Did you say that and I missed it? Are they turning?
Everything is turning, but the spirals do not turn in the way that you think they turn. They can rotate either way, against winding up the spirals arms or unwinding them.
Whoa.
And the ellipticals don't have any bulk single motion. They are a bunch of sort of randomly orbiting stars.
Like a cluster of bees.
Yeah, right.
So this is a rich region of faint galaxies in the region. This is the one barred spiral we just showed. And this is our friend, the elliptical. So there's a number of other things around there that are elliptical and some spirals.
Well, did I miss the ratio? How many ellipticals? What percentage?
That's a good question. I don't know. I would guess that it's about 50-50.
Oh.
I think I've seen before that something like 25 or 28% of galaxies are spiral.
Jerry, when you see a galaxy and there's a few that are just look circular, are those ellipticals?
Yeah.
Okay.
Fuzzballs.
Yeah, fuzzballs.
Fuzzballs.
Some spirals will get a bar and others won't. That's really weird. I wonder if we know why.
Or maybe some spirals get a bar and then later the bar goes away.
Yeah.
Oh, okay.
And the type of these galaxies seems to be listed with each one, or at least with most of them.
Yeah.
Does the bar
elliptical
PEC right there, edge on, peculiar edge on.
Yeah.
Well, both spirals. Go ahead.
I was just going to say our galaxy is barred, right?
Yes.
Right.
Yes.
Okay, Bruce, I'm sorry.
Well, no, both barred spirals and spiral galaxies don't obey the laws of physics as we know them. They
all
don't.
do.
Pardon?
They all do.
Yeah.
Well, no, the spiral galaxies are more as though the stars are fixed into a flat plane of plastic or something, and it
Yeah.
all rotates as a unit. And over long periods
No.
of time, they drift apart.
No, that they don't rotate as a unit. They just don't meet the distribution of velocities that you'd expect using Kepler's laws of motion and
Okay,
Yeah.
you're right. I mean, I was trying to say the same thing less eloquently.
Well,
and
can
that's
I
where we
make
get
it?
the dark matter.
Exactly.
I'd like
The
to. I'd like to make
stars
a.
are about half of 1% of the known matter in the universe. The stuff we can see is about 5%. The rest is dark energy and dark matter.
Well, gentlemen, if you don't mind an announcement, I just booked our May 2nd speaker for the next month following this Friday night. Lady professor from Cal State San Bernardino,
Okay.
Dr. Katie Wimberly, and her topic will be dwarf galaxies.
All right.
Oh, yeah.
So that'll be interesting to see how that fits into this scheme
We
here.
talked about that 2 sessions ago.
Well, we did dwarf
Yeah.
galaxies.
Yep.
Okay. Here is the early morning sky.
Mhm.
This is 4:30 in the morning. If you have a flat eastern horizon or southern horizon, I mean, because the summer constellations are coming up. We're starting to get in the landing pattern for this summer sky. There's Sagittarius over there, the teapot, perfectly aligned with the spout. And out of this comes the Milky Way, or it looks like it does. But we're going to look at Scorpius here. There is in the tail, there's M7, which is this right here. So you can curl around there and just keep going. And visually, that's how you can star hop to M7. So you move your scope this way.
Yeah, or less south than Shala, pretty much
Yeah.
pretty close to it. The Stinger stars.
Now, this region of the sky, it doesn't show it here, but this region of the sky is very rich. You're looking toward the center of the galaxy, which is right up in here. So this is full of star clouds. And M7 is a small open cluster. It's not a globular cluster.
One of Tom's favorites.
Yeah.
Oh, okay.
M6 too, the butterfly.
M6
Yeah.
as well, yeah.
Okay.
M6 and M7.
So this is a wide field view that shows all the rich star clouds in the background of the Scorpion. And these are dark nebulas. They're not missing stars. These are blotches of gas and dust that are in front of the star clouds, but they're not being illuminated or made to glow by a rich or a hot star. And this little jewel box in here, that's the cluster M7. There's only about 100 stars in there, if I recall.
Dark clouds. It's the first time I've ever heard that phrase.
Dark nebulae, Ron. We've
Yeah.
covered those before.
Yeah.
The horse head and stuff like that.
I've heard nebula many times in star clusters, but star clouds, I've never heard it. I'm sorry.
Sure.
Well, dark clouds.
There's one in this There's one in this area, Ron, called the ink spot. That's
Yeah.
really,
Mhm.
the first time I saw that, it's as black as I've never seen.
Yeah.
I've never seen a black like that.
You see,
Really?
you see the ink blot on a lot of pages that are trying to make a mystery about holes in the galaxy and missing stars.
Yeah.
Because they don't understand that it's just a cloud of dark matter, or not dark matter, excuse me, the wrong misuse of words. It's a dark nebula in front of the stars, but they're all over here. These are just wisps of nebula that are not illuminated.
Although there is a spot in there called Bada's window where it actually is kind of a gap that you can look farther into.
Mhm.
Huh.
Yeah, it has this star cloud in the core of our galaxy has irregular edges, so it'll be little swirls on the edges and stuff too. So at one point, when they started developing telescopes that were of higher quality than Galileo's poor little instrument, a lot of these nebula that they saw, the faint fuzzies, they were able to resolve them into stars, globular clusters and open clusters. And eventually they thought that all these things would, if you could magnify them big enough, they would all be resolved into stars. But that wasn't true. It took the really big telescopes in the 1800s to look at that and realize that there are some clouds of just gas.
Well, isn't the Coal-Sack Nebula one of those?
That's
No.
in the
One of
southern,
them, I don't think it's in this field of view, but there's one called the Coal-Sack Nebula.
that's in the southern hemisphere.
Yeah,
Okay.
yeah. This one's sometimes called Ptolemy's cluster, M7.
Yeah.
Now
And
we'll later
they
on
don't show this, but there is a globular cluster off to the left of M7 that you can get in an 8-inch easy.
Is it in this?
I can't see it in this image.
Is it up there? That looks like a globular cluster.
Yeah, depending on what's east and west in here, that might be
Yeah.
it.
That could be the one, Chuck. Yeah,
Yeah.
I've seen it my 8. Okay.
Okay.
And M7's naked eye here. So
Yeah.
Out over the ocean, yeah.
yeah.
Yes, we get very, very dark skies out over the ocean.
Mm-hmm.
No
Well,
one lives
can
out
I
there.
May I express something about gas and dust in space?
Go ahead.
Supposedly there's 3 or actually 4 types of matter, but do they only exist down here in a warm atmosphere? In other
No.
words, gaseous, let's say water, evaporates, and the molecules separate in space. Can matter be solid? Can it
Yeah.
be liquid? Can it
Yeah.
be? It's always a gas.
No.
Well, that's what they say, gas and dust.
Well, the dust is solid matter.
Yeah.
Okay. Can they be droplets?
Yeah.
Yeah. And they can be individual atoms that haven't formed a molecule, or they can be individual molecules.
Because every element can become all 3 states, right?
All 4 states.
Well, four when they're plasma, when they're a fire. Well,
Yeah.
I'm just curious.
See, ancients had it almost right. If they claimed that the 4 elements were earth, air, fire, and water. But if they'd have just said, instead of elements, if they just said phase, then they would have had it right.
Huh.
Because
Right.
that's the 4 phases of matter, solid, liquid, gas, and plasma.
Yeah.
Or
Well,
at least
that which you could
grossly
not
evident
see.
ones. Now there's all kinds of other little semi-phases that people talk about.
Dwarf
Right.
phases, yeah.
Yeah.
Right. And that which you couldn't see was called the quintessence.
Well, that's what attracted me to solid state physics or condensed matter physics, is that in the confines of a solid, you get all sorts of weird particles that aren't real particles, they're quasi-particles,
Right.
which means they're collective effects of the particle and the matrix around them. But very, very exotic situations. I think it's almost infinite what particles you can find in there, quasi-particles. Anyway, this is April 4th. This is Thursday, I think it is.
Sounds
Or
like Friday.
Yes.
Friday.
Yes.
So this is the moon at first quarter. It's right near Mars. It's pushing its way in between the two twins.
Fourth is Friday, Jerry.
That's what the 4th is Friday. Thank you.
Friday, yeah. It's the
Yeah.
meeting.
Now look at
Yeah,
the
it's our
clock
meeting
in the
later, yeah.
upper left corner.
Now this is 7:15, so our meeting, we will be in the observatory or the planetarium halfway through Chuck's talk on the stars, with the meeting about to start at 7:30.
And depending on the audience, hearing the same jokes.
Right.
Over and over again.
Yeah. If there's not a lot of the public, then you won't have to listen to the same old jokes.
Mhm.
Okay. So this is our cut in half moon at first quarter. And when I saw these things as a kid, they always reminded me of those March of Dimes card that you get, that you stick
Yeah.
a dime in the
Right,
slot.
right.
And so I don't think they do that anymore.
Yeah.
No, they don't even vaccinate anymore.
Yeah, that's right.
Uh-oh.
So we
Tim,
gotta-
looks
yeah,
like
I'm
you're
not
coming
gonna-
down with the measles.
Yeah.
The what?
It looks like Tim's coming down with the measles.
Like, yeah, even behind me.
Yeah.
Hey, it's Boeing.
Now, this is a photo taken from the ISS
Mhm.
of Boeing's Starliner decoupling from the ISS and heading back to Earth.
Hmm.
And it made the flight okay. The problem was helium leaks in the helium system, which we can forgive them for, because if you've ever worked with helium plumbing, helium is a little tiny inert spherical molecule or atom, and it goes through just about everything. So it's almost impossible to contain. You have a big steel cylinder of helium, and eventually the helium will all leak out of it. But
Really?
to get a helium plumbing that doesn't leak is a heroic job. Unfortunately, they didn't have any heroes putting it together. So they're re-examining that with a lot of putty and tape and everything, and make sure they got all the leaks fixed.
Is
So-
the helium used to adjust retro rockets, things like that?
It's used as an emission. It's inert, but it doesn't burn, but it's used as a pressure for the jet.
So
It's-
something's got to spray into space.
Yeah,
Yeah.
that, yeah, so they're spraying out helium.
Yeah.
That way it doesn't react, if they come near the ISS, it's not going to mess with any instruments that are there by coating the lenses and stuff like that.
But NASA didn't use that on Apollo, for example.
Yeah.
They
No, they
did?
use hypergolics, I thought.
Yeah, I think you're right on that, because there wasn't anything up there to try and dock with at first.
So why doesn't SpaceX have a problem with that?
I don't know whether they use helium or not. They probably do. I think they just did a better job of sealing their helium leaks.
Huh.
You have to, it takes special care to make sure that all your doors are bolted on and your helium is all sealed in. And so they're just going to have to redo it again. I would
Well,
say
from your-
Boeing has
I'm gonna
temporarily
be
lost its
interested in-
mojo.
I'm going to
But
be
they
interested.
need this, they need the second backup so that they can have ways to get up and down without relying on the Russians, the Soyuz.
Tim?
Well, don't hypergolics have an interior rubber bladder or something like that with a gas like helium on one side, so that the liquid is all pushed off to the bottom where they want it, because there's no gravity to pull it down there.
I think they have two separate reservoirs.
Yeah, you guys are talking beyond my knowledge. I don't know.
Well, where do they get helium? I used to hear that it's
You
running
mine
out,
it. It's a byproduct of natural gas
Natural
mining.
gas.
so they can make it.
The US has the largest source and supply of it. It's
Yeah,
a
they-
critical, what do they call
Strategic
that?
material.
Strategic mineral. Yeah,
They just found a big deposit of it in like Minnesota or somewhere.
yeah. For some reason, the US is blessed with it, and we used it in grad school, like going out of style.
Yeah, now all the Minnesotans sound like Mickey Mouse.
Yeah.
So the way we thought of it was, our professor told us, when you use liquid helium, consider it to cost what fine cognac cost.
Yeah,
Liquid, huh?
Yes, it's very cold, 4 degrees Kelvin.
4 degrees, right?
yeah, we used to
Holy
condense it. We used to condense it at the University of Arizona, so we could do our cryogenics.
Yeah,
Wow.
They did. And it doesn't bond well with other elements to make compounds.
no, it's completely inert.
It's inert.
I think someone has succeeded in bonding it with fluorine.
Wonder what they call it.
Super
Is it
glue.
po- is it
Super glue,
poison?
no, it's not.
Helium fluoride.
Yeah,
And Ron, why is it called helium?
I don't know.
It's first found on the sun.
that's right.
From the
Found
sun.
spectroscopically.
Yeah,
Then it was isolated on Earth.
Helios, sun in Greek.
Ah,
Oh, okay. But it's a strange little
Yes,
element with
it's
two
not a masculine
protons.
element.
Yeah.
Got 2 protons. Does it have any neutrons in there?
Sure.
Yeah,
No,
the heavier version of it.
yeah, helium-4.
hey, Jerry, can I ask, are you going to be covering, if you're going to be covering this in the next couple of sections, you mentioned in the talking points that they want a recovery vehicle, and that SpaceX being a recovery vehicle for the, Boeing one,
Yeah,
that's going to be reversed. The Boeing one will be a recovery vehicle maybe for
No,
SpaceX.
the whole idea is just to have two, so you're not totally reliant on one if they find a flaw.
yeah.
Okay, it just sounded in the talking points, it sounded like the Boeing one can be up and running really quick.
They think so.
Yeah.
Yeah.
Once they're-
Okay.
Once it meets specifications, it'll be fine.
Okay.
But
Okay.
wouldn't they do a test flight to prove that it's going to meet the specs without any people on board?
Yeah, that's the next plan. NASA's plan is to do one flight to first to catch it up, then verify it in the ground lab that it's okay, then do one test flight without any people in it, and then the next flight after that will be another people launch system.
Okay.
But they'll pack extra underwear on that one.
Yeah,
Okay.
Well, they've really had some
they'll
bad
have
press.
parachutes.
Yeah.
Okay. Thank you, Jerry.
Okay. Well, there's a mission called HERA, HERA, and it's headed out toward Dimorphos. It's going to try and take pictures of and study the crater and the damage that it did when it slammed into Didymos, when our previous probe slammed into Didymos.
Well, they slammed into Dimorphos. Didymos
Okay.
is the major component.
Okay, sorry. So anyway, it just passed, to get a little boost, it passed close to Mars, and when it did, it happened to take some pictures of Deimos. This is Deimos, and this is an thermal infrared imager. So this is lighter stuff. You can set it up so that just by flipping a switch in these, because the infrared cameras do false color and false black and white. So you can have white hot or black hot. And this, I think, is a black hot picture of Deimos. Let's see, does it
No,
say?
yeah, Deimos. Yeah.
A negative?
Basically, well,
In other words, the rock was white and the background was black, and they
No,
just
no, no.
reversed it.
It's just what is hot and what is not hot.
And you can switch it willy-nilly. So they didn't say which one it is here, but it looks to me like the Deimos is probably the hot object. But I don't know. Yeah, here it says the warmer surface of Deimos versus Mars below it. So in this one, black is hot.
Black is
But
hot.
when they show you some car thief trying to run through the bushes to get away, they usually make it white hot. So you can, it makes more sense to people seeing someone's body temperature as hot. This is another picture taken with another camera.
And definitely false color.
Yeah, definitely false color.
yeah, it's not a red planet.
Yeah.
No, not in this one.
Hmm. They're tiny, aren't they? Mile or two, less than a mile across?
No, 7 miles across for Deimos and 13 for Phobos.
Oh, okay.
Mhm.
And the prognosis for them, they're heading out or they're
No,
going to go away?
the prognosis is they're testing the cameras as they go by. And it's
Well-
cool. You don't usually get to see pictures of Deimos. So that's why I put them in here, just because they're cool pictures.
But Ron, I think, was asking about the fate of the moons. And Phobos is going to
Oh.
crash into Mars. Deimos seems to be moving out, I think.
Yeah.
Like ours is. Okay.
And here it
there we
shows
go.
brightness temperature, it's scaled. So this is hotter than any temperature that's recorded on the surface of the planet. Up here, this is bright is hot. So this is contrast to the previous two, which showed dark is hot.
Hmm.
So that's a test of 3 of the cameras that they have on board. So they're ready for Didymos. Okay. Now, someone asked Astronomy Magazine, because Sirius is a nearby star, giant star with a white dwarf companion, the dog star here and the pup here, and someone asked, when will this thing blow up as a supernova? Because they know that the white dwarf can drain hydrogen from the giant star, until enough accumulates on the surface that its temperature rises and it starts to fuse. And when hydrogen fuses, it becomes a hydrogen bomb. Well, it's not ever going to happen for Sirius because you need to be, in order for now this is an artist diagram, this is not a photo, but here's the giant star having part of its atmosphere, the hydrogen, taken off gravitationally by the white dwarf, and it's accumulating around the white dwarf until it collapses down onto the white dwarf. But you see, this is just a few diameters of this star away. In the case of Sirius B, oh, by the way, it's 8.6 light years from us, but they're about 7 astronomical units from each other. So 7 times the Earth's distance from the sun. So in Sirius case, this star is way too far away. Here it would have to be looks like about 2 or 3 star radii away. In this case, it could happen. You could get a flare up, a supernova from this. But in Sirius A and B, you're not going to get anything.
And T Corona Borealis still hasn't gone nova.
Yeah.
Yeah, I looked at that.
Yeah.
We're going to skip ahead for the moment because we're running out of time. But we're going to go back to, maybe.
But we still got almost half an hour.
Yeah.
Yeah.
So anyway, we're going to look at 30 years
24
of
minutes.
exoplanets. This is an illustration of a super Earth in a planetary system whose central star is a red dwarf, way up here. Super Earths are larger than our planet, but smaller than Neptune, with masses up to 10 times that of Earth. Now, if they do find an Earth, and it's a super Earth, it's going to be very difficult for that civilization, if it supports life and they develop in advanced intelligence, difficult for them to have a space program. Because look at the fuel it takes for us to get off of the mini Earth. They're going to have to build gigando rockets just to get in low Earth orbit. So that may limit them. But let's see, where was I going with this? Oh yeah, this is another artist impression. Shows 51 Pegasi B. The star is 51 Pegasi, and this is B. The first exoplanet discovered around a sun-like star. It lies about 50 light years away and orbits only 5 million miles. So our Earth orbits at 93 million miles. So their astronomical unit is much, much smaller than ours is.
Well, they don't think life could exist on this sucker.
No, pretty hot. It's a
Yeah,
hot
Pretty
Jupiter.
hot, yeah.
So over the last 30 years, I think there's about 4,000 to 5,000 verified exoplanets now.
Yeah, it's up over 5,000. Yeah.
Yeah, okay. And there's about 10,000 in the list waiting to be verified. So the 2 primary measurements that do it are radial velocity and transits. And the radial velocity measurement is super sensitive. And that's how we get a lot of these planets. This shows the central star. In our system, this would be our sun, and this would be our Earth going around the sun. But of course, the Earth doesn't go around the sun exactly. It's that the sun and the Earth go around a common center of gravity, which is this X. So the sun, which is very bright and you can see it, and the planet, which is not so bright and you cannot see it, but you can see the motion of this star as it comes and goes. So when it's coming this way, the spectral lines here, this shows the spectra of the star right there. And when it's coming toward it, it shifts these features to the blue. So this is the blue line. So this is a Doppler shift to the blue. And you see the star. Now this is extremely small wavelengths. We have excellent instruments to do this detection. So you can see this. If there's an Earth orbiting a sun, you can see this effect on the sun. And going the other way, when it's at the other part of the orbit, the sun is moving this way, the Earth is moving this way, and now the same spectral lines have shifted to the right, to the red. So this is a very small change, but we can easily detect it. Now, it does have to be lined up so the motion of the sun is toward us and away from us, mostly, but it doesn't have to be as critically lined up as it does when you're doing a transit.
You know,
So this one, go ahead.
decades ago, when these planets were first coming out, the Kavli Institute had Jeff Marcy come and speak, and he was one of the, big early planetary transit discoverers. And he was talking about this radial motion, and I happened to be in the audience, and I raised my hand, and I said, well, a lot of stars pulsate with a regular pulsation. How do you distinguish pulsations in the star's atmosphere from actual physical motions of the star around the common center of gravity? And he got super pissed off. He said, who told you to ask that question? Who put you up to it? And I was like, excuse me. And I tried to get as small as possible. But apparently that was some kind of critique of some of his measurements.
Mm-hmm.
And it was a sore point for him. And I happened to
I guess so.
push the wrong nerve.
Did he ever finally answer it?
No,
Oh,
no, he just went on.
well, let's send him a note.
Yeah.
Yeah.
Well, in effect, are you saying that we affect the sun a little bit and there's a
Yes.
dot in the middle of it that we both orbit around?
Yeah.
Yes.
Yes, yeah.
In our
Jupiter
case, it's
does-
inside the surface of the sun, but it's not
Right.
at the center of the sun.
Yeah.
Right, and Jupiter does the most.
Now,
But all 9 planets, all 8 planets would have their own, wouldn't they?
yes, they do. But and what you see in a solar system where there's multiple planets like ours, you see a complexity of blue and red Doppler shifts.
Right.
Because each
Right.
one, Jupiter would be the largest effect on our sun, Saturn and
Right.
Neptune, Uranus, another, and
Yeah,
the
Ron,
smaller stuff
I
inside.
could- when I was teaching at Westmont, Ron, I had the students calculate what Jupiter's influence would be on the sun. Okay, and it makes our sun go around a little circle about 5 meters a second, just roughly that.
So its center of gravity in the sun would be outside of the sun?
Oh, no, it's inside. The center of gravity of the system's inside the sun.
It's just
Yeah,
out of the sun in this illustration for illustrative purposes.
Right.
So, but there could be a very big planet or even a double star system where they
Mm-hmm.
rotate around a common center of gravity that is outside of the sun, of that star.
And the bigger the
Could be.
planet is, the easier it is to detect this because of
That's
that
right.
motion.
Right.
And that's why the first bunch of planets that were found were all these hot Jupiters.
Yeah.
Right.
So,
Well,
but
are
you even when there's multiple planets, you have to get several orbits. And if you're, for example, looking at our system, Jupiter takes 12 years to go around.
Right.
So you've got to do several go-arounds to see the whole thing. So you're going to be talking about 50 years of observations to get, the data right and the signal to noise big enough.
Yeah, and all the
Yeah.
planets will give you like a spectrum of frequencies, if you
Right.
like.
And
Yeah.
we can deconvolute.
You can, decompose
So
those.
we
Yeah.
can look at the individual components,
Mhm.
but it
Now
takes
that's
time.
something, this must be an article from Astronomy Magazine, because they're saying, you need at least 3 transit observations. So a Jupiter-sized planet in a Jupiter-sized orbit would take at least 10 years to get that.
Yeah.
Mhm.
And it's like, what? Because that wouldn't give you the 3 with
No.
Jupiter, at least not in our system.
No. So it's either from astronomy or Sky and Telescope. I think it's Sky and Telescope.
No, Sky and Telescope wouldn't make an error like that.
Okay. Well, there's no error in this chart.
Yeah.
So
Wasn't there something that bothered Isaac Newton about what they became known as the 3-body problem?
Well, that's just math. That's
Yeah,
They're
Well,
not
I thought-
stable.
It was about orbits, wasn't it?
Yes.
Yeah.
The minute you get three bodies orbiting, you can't calculate anything.
you can't
No, you
calculate
can.
them in closed form, but you can do it numerically. He didn't have numerical computation techniques available.
Right.
Oh, it's
And the
fascinating.
presentation we gave on the my simulation of 39 planets and moons, what was that, about 3 or 4 years ago? The sun moves about equal to its diameter in a simulation I did for 5,000 years. You know, just the orbit. It's not, you know, it's never always out there. It just wiggles all over the place.
Really? Okay.
Okay, so this is a montage. Kepler 90 is a star with 8 exoplanets.
And we know the size of them already.
Yes, the talking points explain how they get the size, the mass, and the radius and stuff, all from these data reduction. But this shows our solar system, the planets of the entire thing. They're missing one out here. And the one of Kepler 90. So they start from the sun. The sun is Kepler 90. This is Kepler 90b. This would be what was our sun called? Sol.
Soul.
This would
yeah.
be Sol B.
Well, actually, probably Jupiter would be that if you were discovering it from far away.
And then as they discovered more, they'd start changing the lettering.
Yeah.
Yeah. So anyway, this is Kepler B, C. Oh, I don't know.
CID. So it depends on the order in which you find them.
Yeah. So that's I. Then there, because there's D, A, B, C, D, E, F, G, H, I.
Hmm.
So this is an oops star.
Yeah. And, you know, and the narrative in there says we've found up to a 6-planet system, and then they show an 8-planet one. So that's kind of weird.
Yeah.
Now, would I be discovered because of calculations?
Yeah. All of them would be.
Okay. Well, I'm just saying that they didn't see it, but doing the calculations, they said something has to be here.
Yeah. They see anomalies in the other orbits, and they
Yeah.
say, oh, wait a minute, this will explain it.
Okay.
Now, sometimes when they do this, we have a picture coming up a few times where it shows direct image by JWST of a planet. But that planet is the only one in that system. But previous to that, from math only, they derived that there were 2 planets in that system that were smaller. But now that we have direct image, we know it's one. So sometimes your image can go, your calculations can go awry. These are right at the edge of what we can detect and see.
Are the 6 smaller ones on the left for Kepler, are they all Rockies?
Probably.
They look like they're rocky, yeah.
And the 2 big ones on the right are like Jupiter and Saturn and
Yeah,
Uranus.
Saturn, Jupiter size, and then these are the super Earths. The size if they're smaller than Neptune, they're a super Earth. So this one looks to be these all 3 look smaller than Neptune.
So it doesn't look like you can have a rocky planet the size of a Jupiter.
Well, that's kind of an assumption we make, but
Yeah.
Well, they're all gas for some reason.
our assumption is that when they grow to a certain size, they can accrete the gas very quickly and hold on to it.
Yeah.
But
Definitely
we
hold on
don't,
to
you know,
it.
you can't say that's absolute.
Okay, there's a rocky inside every one of them, then a little rocky planet that's
A core,
That
yeah.
was the thought at first, and it might be true, but now they think that they think that in the case of Jupiter, that there's no solid surface transition between the solid center and the liquid layer outside, farther out. It's a continuum of densities.
That the rocks are kind of dissolved into this metallic hydrogen
Right.
stuff that's in there.
So
But
even
it
though there's
starts
a
out as a
solid
rocky
core,
core, most likely.
there's no surface on the solid.
Yeah.
But I wonder if there's any giant ringed ones like Saturn that the Webb might be able to see. Would they be able to see the rings?
They
Of
do
a
see rings, and they see protoplanetary disks that are rings around stars.
Oh, they do. Oh,
Yeah.
Rings appear to be fairly common. We found a
Yeah.
whole bunch of asteroids that have rings even.
Yeah. And our Uranus and Neptune both have rings, and so does Jupiter.
They're not
Just-
Dyson spheres, are they?
No, that's around a star.
I think Dyson spheres are completely fantasy.
Yeah.
Yeah, it's a lot of
Because-
work. It'd be a lot of work to make one, I would imagine.
Well,
Yeah.
they're gravitationally unstable too.
Yeah, they're gravitationally unstable. Also, where do you get the material to make one?
Yeah.
If you had that much material, it would become it'd fuse on its own weight, just so it would destroy itself. I think that they're not realistic.
So somebody
is
came up with that. All right, that
this is the
fantasy's
other-
going away.
This
Right?
is the other technique for finding them, which is transit. And here you do have to be lined up very closely with the plane of the orbit of the planet you're looking for. And it's estimated that a little less than 10% of stars are oriented this way for us that have planetary systems. One of the reasons that we want to do so much direct imaging, also because for us seeing is believing.
Yeah.
But this shows a planet going around a star. At this point, right here, the planet is going in front of the sun, so it blocks part of the sunlight. So you will see if you're doing sensitive photometric measurements of the star's brightness, you will see the star's brightness goes down as the planet passes in front of the
For the star.
yeah. And then
Like
when-
what
and then
Mercury does to our star, I guess.
Yeah.
yes, and Venus
And Venus too?
on
Okay.
occasion, every 125 years or something like that.
Yeah, it's like-
Transiting.
Yeah.
So here, now as the planet goes around, here we see the dark side of the planet. Here we see the light side of the planet. So it's putting out things. And so its brightness, the sun and the planet together, which we can't resolve. We see the brightness is up here. And then as the planet goes behind the sun, we drop down to the star alone. So we just get the brightness of the star. Here it comes back, and we get the brightness of the star and the planet, full planet phase. And then it goes around again. And so, and this is fairly easy to measure for some stars. We had a girl named Zoe in 2014 that the
Right.
club helped. Her and her dad set up a barn door camera. They showed that what they'd set up, and she had actually captured this curve for a exoplanet system
And
using a
it-
Canon camera.
and if you take a spectrum with the star alone and then a spectrum when you've got the planet in front, you can subtract them and get some of the spectrum of the planet's atmosphere.
Yes. And that goes on. Some planets have water, some planets have interesting components. One planet has some dimethyl something or other in it that's supposed to be I say supposed to be because I'm not an expert in it, but it's supposed to be something that's consistent with plant life. So
Is one more accurate than the other?
one more accurate system.
Yeah, is the parallax more accurate than the displacement of?
You mean
Visual-
the transit versus the spectroscopic redshift?
At first this one was more accurate, but now the Doppler shift, we've developed much better instruments for measuring offsets.
Okay,
There's a technique that I'm not completely familiar with called spectral combs that can measure very slight offsets of spectral lines.
huh.
So I would guess they're comparable. They're both very successful.
Except that
but they're each
except
limited.
the parallax ones, you have to be aligned, and then you said
Well,
there's
wait,
only 10%
this
of them.
isn't parallax. This
No.
isn't parallax, Tim.
It's not?
No. This isn't parallax. This is brightness of the
Yeah,
system.
this is
Oh, okay. Okay.
photometry. And the other one was not parallax either, because you have to see both objects.
Oh, all right.
But what we do with the other one is that we look at the spectra, the combined spectra.
Parallax is about the distance to the star, isn't it?
Yes. I'm not aware that we have any parallax measurements of an exoplanet, but we might. Okay, these are
Well,
the, our
we have parallax measurements of some stars around which exoplanets have been found.
yes.
They're very close, you know, relatively close, 10 light years or so. But that
Okay.
doesn't really tell you anything about the exoplanets.
But
Okay.
what are the odds that we're going to see this stellar system edge on?
Like Jerry
Well,
said, about 10%.
10%, yeah.
10%, huh? Okay.
And that's just an estimate. But
Yeah,
but the fact that we're finding so many tells you the planets are really out there like crazy.
yeah.
Yeah.
Yeah, the ones that don't transit, we know they go around there. We just can't see them.
Mhm.
They'll never obliterate this. Okay, is this our stuff?
This
What
is
are we
all
looking
how we use it to detect.
Oh, of
Look
course.
at exoplanets. We do spacecraft, Hubble, Spitzer, Kepler, TESS, JWST, and the Roman, which is not launched yet, which is going to go out there with the JWST. This co-rot is retired. Gaia, Cheops, Plato. This one,
That's
I'm
a
not
future
sure
one,
that
I
that's
think.
launched yet. I don't see the HWO on here though. which
That's
is-
up there at the top, Habitable Worlds Observatory.
Oh yeah, HWO. Thank you. Yes, this. So and that's yeah. So that's home world observatory. They're looking for Earths specifically. We'll get to that. So here we look. Also, these are primarily spectroscopic measurements from the ground. Photometry from most satellites, because the atmosphere really messes with our photometry.
And doing it with CubeSats is pretty amazing.
Yes,
And some have been retired.
some have been retired. Yes, they've run out of their cooling juice or their orientation fuel, and they just return them to Earth.
Really?
This is one of the first HWO concepts. It's a mirror in here with solar panels out back. And the mirror is the same size as the James Webb Space Telescope and made the same way. It's a honeycomb or hexagonal patchwork. This is an early concept. And this is a more recent, or this is a picture of that same concept. You can see the honeycomb mirror, main mirror back here, and the secondary mirror looking up at it. And then it goes down to instruments here. This
and then
would
the multi-layer heat shields.
This would what?
And the multi-layer heat shields.
Yes, it has a multi-layer heat shield, but this is not intended to take as deep infrared as I believe the James Webb is. It's still going to work in the infrared.
Wow.
This
What's the name of that one?
HWO, the Home World Observatory.
Or Habitable Worlds Observatory.
Yeah, habitable world, yeah. So I'm thinking too close to home there. So that's
This one going to obliterate the sun with that thing on the right?
Yeah, it'll
This
obliterate
thing-
the star that they're looking at.
yeah.
Oh,
This is a coronagraph. They have here the cleaning ladies going by my office right now. So this is the HWO here. Now this is still in the concept phase. It's probably going to be launched around 2040 if we still have a NASA.
Yeah.
So this is and this is a disk that's going to float in formation out in front of it that will be moved to block the star so we can do direct imaging of planets around the star. Usually we put the so far we've put the blockage disk inside the telescope. And we use it as amateurs. We use that if we're trying to, for example, look for the pup star. We put a piece of fishing line across our eyepiece focusing tube, and then we move it so Sirius is blocked behind the width of the fishing line.
Wow.
really?
Wow.
A little self-occultation there, huh?
Yeah.
Okay, now
Sort of a little do-it-yourself occultation.
Exactly. How big is that thing that's on the right, that star?
This thing, it's in proportion into scale, and the mirror in here is the same size as the James WST mirror, which
So
I
it's going
forget
to
how
back,
big it is.
so it's
9
big
meters.
enough that you can back off from it miles and
Yeah, I
Yeah.
think here the distance between them is not to scale, even though the sizes are to scale.
Right.
but they're going to be launched together and somehow separate, I guess.
Yeah,
Yeah.
they're going to fly in formation.
Wow.
And that
And
requires
there's
really
also plans
precise.
for a gravity wave telescope, which is like the big ones. They have mile-long laser beams at several
4
places.
mile long.
They're going to do it in space with satellites that fly in formation very accurately. Now, this is our last quick shot. This is a
Okay.
constellation you will never see from here. This is Indus in the
You can see
southern.
Bruce. You can see Bruce here.
See what?
You can see Bruce the crane.
Oh, yeah, Bruce. Yeah. And Tucana.
Yeah.
They don't serve 47 Tucana, probably down there. But
Yeah. Anything
Bravo
below
and
minus
Telescopium.
56, Jerry.
What's that?
Anything below minus 56, you can't really see here.
Yeah. So
Got it washed out.
we're looking at Epsilon Indus here.
Mhm.
And this is a direct image from James
Wow.
Webb Telescope.
Hmm.
And this is the occultation disk that JWST has. And this is its planet. So this is direct image of a very large planet
Wow.
called around Epsilon Indus.
Which is just below our horizon.
Yeah, yeah. Not even
Does
from the
the
gun club can you get
occultation
this.
Does the occultation disk basically go near the surface of the sensor?
I think it's probably somewhere more out in the path.
Wow.
I was thinking about the diffraction lines that it would create.
Yeah, yeah.
That's why it has those spikes, radial spikes, the scallop
Oh,
edge, is
okay.
to avoid diffraction patterns.
And,
You
and
try to
that'll-
create your own diffraction pattern that will mess up what a normal disk would give you.
Yeah. Okay, well, I guess we don't have time to go back to the nukes.
No, we'll put that on the calendar for next week if you want,
Yeah.
gentlemen.
They're actually all in the far future anyway.
Yeah,
I've wondered about that because I think Voyager is still running on plutonium, isn't it?
it
Yeah.
is, but there's a world, because of all the treaties we have against nukes, there's a shortage of usable plutonium, and they're running out of it.
But I've heard that the problem is launching. If it happened to crash,
No, there's a lot of public outcry when they heard the word nuclear.
really,
I think it's unjustifiable. It's an emotional response. Of course, you do have to take precautions, but engineering can handle it. So they launch these things with plutonium in them, but they just don't tell anyone.
And
we have
they
the
are
last-
armored. They're armored against kind of a
Yes.
worst case collision.
They have taken precautions.
And we're living just down the coast from the last nuclear power plant in California, gentlemen. Well, that does it for number 213, everybody. Join us Friday night at the museum for a trip out to the black hole, the explorer, the edge of the universe with Joseph Farah. We'll see you back here a week from today for number 14.